So this will be the first lecture over chapter 9. So chapter 9 is over alkynes. So if you remember what an alkyne is, it's any molecule that's got a carbon-carbon triple bond in it. So we'll look at how to name alkynes and look at the basic acidity of alkynes. Okay, so if you have an alkyne, so let's just take a couple of examples. So those are both C4H3, 4, 5, 6, C4H6. So both alkynes, 4-carbon chain. So this would be what's known as a terminal alkyne, since the triple bond is at the end. So it has a CH on it, has a CH on the triple bond, or has a hydrogen on the triple bond. Whereas this would be an internal alkyne. So in this case, the triple bond is between 2 carbons. Okay, so if we were to name these 2 alkynes, so we would start numbering 1, 2, 3, 4. So 4 carbons would be butane. And to name that as an alkyne, we're going to change the ANE ending to YNE. So this would be, and then we're going to put the number right before that so that you know where the triple bond starts at. So this will be but-1 ine. And this would be 1, 2, 3, 4. So that would be but-2 ine. Okay, so let's just take a few more examples. Okay, so we'll take that and take a molecule with an alkene and an alkyne in it. So if we name these 2 molecules, so of course, if all you have is an alkyne in the molecule, you would want to number the carbon chain to keep the alkyne as low as possible. So in this case, 8 carbons would be octane. Change the YNE ending to ANE ending to YNE and put the number right before it. So that would be oct-3 ine. And in this molecule, when you have an alkene and an alkyne, then you have 2 different functional groups. So now you have to know which one has priority, and the alkene has priority over the alkyne. So 7 carbons, so it's going to be based on heptane. And okay, so then you would typically change the A to E to name the alkene. So hept-1 N, and then when you have both an alkene and an alkyne, you keep that part for the alkene and just change the EN into YNE. So hept-1N 6 ine would be the way that you name that molecule. Okay, so some alkynes have a very common name. So that's a very common alkyne that has lots of industrial use. So technically this would be 1 carbon, 2 carbon, so this would be F-ine. And obviously you don't need a number in this case because it has to be at carbon number 1. This would be more commonly known as acetylene. Not historical, I'm not sure where the name comes from. Obviously that would typically mean alkene, so I have to look this up. Why is that called acetylene? But this is a very common molecule. Maybe some of you have heard of acetylene before. This is used in welding. Right, because when the flame burns at extremely high temperature, so you can use it to to melt metal and iron and weld with it. Okay, so that's it for naming alkynes. Let's look at their basic acidity. So for terminal alkynes, so usually hydrogens on carbon are not that acidic, but in the case of an alkyne, the terminal hydrogen is relatively acidic. Right, it's not acidic like hydrochloric acid, something like that, but it's acidic enough that you can pull the hydrogen off with a fairly strong base. So if we compare now alkyne to an alkene, and to an alkane, so if we were to remove a hydrogen from any of these carbons, so if we remove the hydrogen with a base, so take a lone pair on a base, make a bond to the hydrogen, and the electrons in the CH bond become a lone pair on carbon. So that would be the conjugate base of an alkyne. Or if we did the same thing with an alkene, so if we took off one of the hydrogens from the double bond, or an alkane, so some base takes off a hydrogen, okay, so which of the conjugate bases is more stable? So the one that's more stable is going to come from the more acidic molecule. So the main difference here is that in this case, that's an sp hybridized carbon. That's an sp2 hybridized carbon. And that's an sp3 hybridized carbon. So where would the lone pair of electrons rather be, on an sp, sp2, or sp3 hybridized carbon? So if you recall, how do you create sp hybridized orbitals? So you take an s orbital and a p orbital and mix them, and you make two sp3 hybrids, or two sp hybrids, right? So how much s character does each one have? Well, you took an s and you took a p, took a 2s and a 2p orbital and mixed them, so each of these, and created two new orbitals, so each of these has 50% s character to it and 50% p character to it. So whereas in sp2, then you took the 2s and you took a 2px, for example, and 2py, for example, and then you created three sp2 hybrids. So each of these then has 33% S character and a little over 60, around 66% P character. For sp3 hybridized, you took the 2s and you took py and you took 2px and you took 2pz and mixed them or hybridized them to get four sp3 hybrids out, so each one has 25% S character and 75% P character to them. So the basic point being, so you have a lone pair of electrons on each of these hybridized carbons, sp, sp2, or sp3. Where would that lone pair rather be? Would it rather be an orbital that has more S character or more P character? And so if you remember from General Chemistry 1, where electrons most stable at, they're more stable in s orbitals than p orbitals. So the electrons lone pair would rather be here. Right, because it's got more s character. So then in essence, those lone pair of electrons would be more close to the nucleus of the atom, and the nucleus of course has the protons, and so that would be a stabilizing interaction. So it's so the basic point being is, in terms of acidity, Alkynes are more acidic than alkenes, which are more acidic than alkanes. So pKa for an alkyne, do I have this in my notes? Let's hope I have that in my notes. Yes, pKa is around 26. For an alkene, pKa is around 45, so they're not very acidic. And for an alkane, it's not acidic at all. It's got a pKa of about 60. So for comparison purposes, if you had a carboxylic acid, their pKa is around 4. If you have an alcohol, that hydrogen's pKa is around 16, which is comparable to water. pKa is around 16. So the alkyne's pKa is only 26, so it's not that acidic, but it's acidic enough that if you have a strong enough base, you can remove it. So would hydroxide be a strong enough base to remove it? So if you took a hydroxide molecule, lone pair, and it removes that hydrogen, then you would make water and the conjugate base of the alkyne, but this has a pKa of 26 and this has a pKa of 16. So where does the equilibria lie? So the equilibria would lie far to the left, right? Because water is more acidic than the alkyne is. So you need a little bit stronger base than that to remove the hydrogen. So if you took an alkyne and reacted it with NH2 minus, so I'll take a lone pair on that, which removes the proton. Then you would make a molecule of ammonia, and ammonia has a pKa of around 36, and this is pKa is 26, so the alkyne is more acidic, so this would greatly favor the products, the reaction going forward. So if you want to take the proton off of an alkyne, you need a very strong base. Like sodium med. Will do the job. Okay, and so we'll use that in the next lecture, because if you remove the proton from a terminal alkyne and you make this molecule, well, the significance being now is that now you have a nucleophilic carbon. And so you can use that to do chemical reactions to make carbon-carbon bonds. So these deprotonated terminal alkynes, so that's a nucleophilic atom, and it's a very good nucleophile. So it can do SN2 reactions, and that's some of the reactions that we'll look at in the next chapter. So now you have a negative charge on carbon with a lone pair. All right, that's what's called a carbanion. Okay, so we will stop there, and in the next lecture over alkynes, we'll look at the reactions that alkynes undergo. We'll look at how to make alkynes, and then in the third lecture we'll look at the reactions that alkynes undergo.